So let us apply Kirchoff's laws to circuit A. Now the first thing we will do is to label the circuit. So we label the circuit A, B, C, D, E, and F. Now having labeled the circuit, we'll now choose a closed loop to traverse, right? So we're going to say we're going to traverse loop A, B, E, F, A. So closed loop, we started A, B, E, F, A. So that means we're going around this loop, or we're traversing this loop in a clockwise direction, right? Now let's examine the circuit and apply Kirchoff's laws. So let's see how we can apply Kirchoff's first law. Remember that Kirchoff's first law says that at a junction in the circuit, the total current flowing into the junction must be equal to the total current flowing out. So if we examine junction B, currents I1 and I2 are flowing into junction B, current I3 is flowing out, and therefore according to Kirchoff's first law, I1 plus I2 is equal to I3. So by Kirchoff's first law, we see that I1 plus I2 is equal to I3, right? Now let's apply Kirchoff's second law, the voltage law, to this loop. So to do that, first we have to identify how many batteries are in the circuit and find the algebraic sum of their EMFs. So in this loop, there's only one battery, the 5.45 volt battery. So if we start at A and go around the loop in a clockwise direction, we encounter the battery. When we encounter the battery, we reach the lower potential or the shorter leg before the higher potential. And so we experience a potential gain, and this EMF will be treated as being positive, right? So if a charge is flowing around the circuit, it reaches the lower potential before the higher potential, it experiences a potential gain, and this will be treated as a positive EMF. So therefore the algebraic sum of E, so for the second law, the algebraic sum of E would be equal to plus 5.5 volts. Good? And since that is the only battery in that part of the circuit, or in that loop, we'll proceed to applying the second part of Kirchoff's second law. Now starting at A and going around the circuit in a clockwise direction, we encounter this 1000 ohm voltmeter, which is resistance, and through it is flowing the current I3. So because the current, of course, is flowing in the same direction that we're traversing the loop, it is treated as a positive current. And so we have sum of IR is equal to 1000 I3. And we proceed. We come around, reach E, and we go back in this direction. We encounter the 1 ohm resistor through which a current I1 is flowing. And because I1 is flowing in the same direction as we are traversing the loop, it is treated as a positive current, and therefore the PD across this 1 ohm resistor will be treated as a positive PD, right? So whenever we're traversing a loop, if the current is flowing in the direction of that we're traversing the loop in, then it will be treated as being positive, and any resistor through which that current is flowing will have a positive PD. However, if the current flows in the opposite direction to that in which you're traversing the loop, it will be treated as being negative, and therefore any resistor through which it flows will be taken as having a negative PD. So in this case, the current I1 flows in the same direction that we're traversing the loop through the 1 ohm resistor, and the PD across the 1 ohm will be treated as being positive. So therefore this gives us plus I1. So we have 5.5 is equal to 1000 I3 plus I1. But of course, from Kirchoff's first law, we know that I1 plus I2 is equal to I3. And therefore what we will do is to replace I3 with the sum of I1 and I2. So we have 5.5 is equal to 1000 times I1 plus I2 plus I1. We expand the brackets and simplify. What we get is this. 5.5 is equal to 1000 I1 plus I1, that is 1001 I1 plus 1000 I2. And this is our first equation, equation 1. Alright? So that is our equation 1. Now, to solve for I1 and I2, we need a second equation. And to get the second equation, we must choose a second loop to traverse. Right? So, let's choose our second loop. Let's choose loop BCDEB. So let's go same clockwise direction. Right? So we're going around the loop in that direction. So we're going to be traversing loop BCDEB. So as before, we'll look at how many batteries are in that loop and we find the algebraic sum of their EMFs. So if we start at B and we go around in this direction clockwise, we encounter the 1.2 volt battery, the only battery in that loop. But of course, this time we encounter the positive terminal before the negative terminal. So that means we experience a potential drop and the EMF will be treated as being negative. So therefore what we have is the algebraic sum of the EMFs is equal to minus 1.2 volts. So again, in traversing this loop, we encounter the positive terminal before the negative terminal. We basically experience a potential drop and the EMF will be treated as being negative, right? So now to apply the second part of Kirchoff's second law, we need to find the algebraic sum of the PDs across all the resistances in the loop. So going around the same loop in the same direction, we encounter C, we encounter the 0.2 ohm resistor. Now, which current is flowing through the 0.2 ohm resistor? The current I2 is flowing through the 0.2 ohm resistor. But in this case, it is flowing in the opposite direction to that in which you are traversing the loop. And as a result, the current will be treated as being negative, and therefore the PD across this resistor will be taken as being negative. And so we have sum of IR equals minus 0.2 I2. So minus 0.2 I2. And we proceed. Next, we come around and we encounter the 1000 ohm resistor, which is of course the voltmeter. And this time, of course, the current flowing through it is I3. And of course, remember that I3 is equal to I1 plus I2. But of course, I3 is flowing in the opposite direction to which we're traversing. And it therefore will be treated as being negative as well. And the PD across this will be taken as being negative. And so what we have is minus 1000 I3. Right? So what we can do now is to basically equate these two pieces. And so get our second equation. So we can say sum of E equals sum of IR. And so we have minus 1.2 volts is equal to minus 0.2 I2 minus 1000 I3. If we simply multiply through both sides by a negative 1, then what we have now is 1.2 volts is equal to 0.2 I2 plus 1000 I3. Now our first equation is in terms of our currents I1 and I2. So we want to get our second equation in terms of I1 and I2 as well. So we have to go back and then say, but I3 is equal to I1 plus I2. And therefore this gives us 1.2 volts is equal to 0.2 I2 plus 1000 I1 plus 1000 I2. And so what we have is 1.2 volts is equal to 1000 I1 plus 1000.2 I2, and that is our second equation, equation 2. Alright? So let's just write the two equations below each other. So we have 5.5 volts is equal to 1001 I1 plus 1000 I2. And that, of course, is our equation 1. Right? Now, in order to solve these two equations, we will, we'll solve them simultaneously. We'll use a method of, say, what method should we use? Let's use a method of substitution to make I2 the subject of equation 1. So from equation 1, we will therefore get that I2 is equal to 5.5 minus 1001 I1 all over 1000. Right? So we bring this over and then divide by 1000. So I2 is equal to 5.5 minus 1001 I1 divided by 1000. Right? And so we will proceed to solving these equations. So what we have is I2 equals 0.0055 minus 1.001 I1. And we will then substitute for I2 into equation 2. So we'll substitute for I2 into equation 2, and doing that we get 1.2 volts is equal to 1000 I1 plus 1000.2 I2, which is equal to all of this. This is 0.0055 minus 1.001 I1. Right? So we have 1.2 volts is equal to 1000 I1, and then we expand our brackets. So we have 1000.2 times 0.0055, that gives us plus 5.501, and 1000.2 times that gives us 1001 minus 1001.2 I1. So now we have an equation in terms of I1 alone, and therefore we can solve for I1. So, all right, continuing. So we have 1.2 volts equals 1000 I1 minus 1001.2 I1. So when you combine those two, we get minus 1.2 I1. And this is plus 5.501. Right? So we bring over and we solve for I1, and this of course will be volts. So 1.2 volts minus 5.501 volts is equal to minus 1.2 I1. And so we get minus, I'll work that out, 1.2 minus 5.501. We have minus 4.301 equals minus 1.2 I1. And so 1.2 I1 is equal to 4.301. And so I1 is equal to 4.301 divided by 1.2. And that gives us 3.59 amperes. So we get that I1 is equal to 3.59 amperes. Now, if you notice that I1 is actually positive, I1 being positive simply means that I1 is actually flowing in the initial direction we assumed it was flowing. So whenever we assume a current is flowing in a particular direction, if it works out to be positive, it means the current is indeed flowing in that direction. However, if it works out to be negative, then it means that it's actually flowing in the opposite direction we assumed it to have been flowing in. So now that we found the value of I1, let's now go ahead and find the value of I2 by substituting it into this equation for which we had made I2 the subject. And so we have I2 equals 5.5 minus 1001 I1, which is 3.59, all over 1000. And so I2 is equal to, let's work this out. So 1001 times 3.59 gives us that, and we take that away from 5.5. We get minus 3588.1 all over 1000, right? We divide it by 1000, and this gives us minus 3.588 amperes. So I2 is equal to minus 3.588 amperes. Now, a short while ago I mentioned that whenever we calculate a current and it works out to be positive, it means the current was flowing in the actual direction that we assumed it to be flowing in. However, if the current works out to be negative, it simply means that the current was actually flowing in the opposite direction. Now let's examine the circuit and what we have calculated so far. Now I1 works out to be 3.59 amperes. I2 works out to be a minus 3.588 amperes. They're almost the same. So basically what this is showing is that I1, which was shown to be flowing in this direction, is actually flowing in that direction with a magnitude of approximately 3.59 amperes. However, I2, which was shown to be flowing in this direction, being driven by the 1.2 volt battery, was actually flowing in the opposite direction based on the fact that it worked out to be negative, right? So I2 is actually flowing in this direction and flowing through 1.2 volts in this direction, not in this direction as the diagram initially assumed, right? Now, having found the value of I1 and I2, we can then find the value of I3, right? Now, since we already established that I3 is equal to I1 plus I2, when we add these two values, we're going to get a very small number, and this is expected since we do not expect a large current to be flowing through our resistor, right? Or voltmeter rather. And so we can calculate the value of I3. So we can say I3 is equal to I1 plus I2. So this gives us 3.59 amperes plus minus 3.588 amperes. And that gives us approximately 0.002 amperes, right? So I3 equals 0.002 amperes. So what this basically shows is that I1 is actually flowing in the direction we initially assumed it was flowing in. I2 is actually flowing in the opposite direction. And I3 is very small because, as expected, we do not expect a large current to be flowing through a high resistance voltmeter. So really and truly, what is happening is this. The 5 volt battery or the 5.5 volt battery is really driving the current I1. And when the current gets to the junction B, it splits. A significant portion of that current, I2, flows through the 1.2 ohm resistor, and a very tiny amount, I3, flows through the 1000 ohm voltmeter.